Okay, I'm Sungyu, and I am an associate professor in the Department of Electrical Engineering at Seoul National University. So let me briefly introduce our recent study on utilizing long-range interactions to break channel bandwidth limit in topological photonics. The study was published in Light Science and Applications very recently. Topology is one of the most interesting degrees of freedom in physics, and here is a picture for illustrating the concept of topology, as you can see in the similarity between a donut and a cup. As you can see, if you apply a certain type of continuous transformation, continuous deformation to a donut, then you can easily obtain the geometrical shape of a cup. And in other words, if you apply a certain type of errors and noise in the form of the continuous deformation, the shape of a donut is very fragile. Therefore, there have been significant efforts to utilize the concept of topology to achieve the noise-robust behaviors in signal processing and computations. If you introduce a set of physical objects that have distinct topological natures, then you can obtain the transition between them through a significant and discontinuous form of the deformations. Therefore, these physical objects are very robust. This is the concept of topological physics, which enables robust behavior, robust performance in signal processing, in condensed matter physics, quantum computations, and photonics. So in our study, we focused on topological photonics. The major goal of this field is to achieve robust signal transport by utilizing topological degrees of freedom of light. But there is a critical limitation in using topological photonics to signal processing. The trade-off relation between the channel number and the bandwidth of each channel. Because of this trade-off relation, the information capacity allowed by the topological photonic circuit in conventionally two-dimensional photonic circuits are restricted. And as you can see, if you increase the channel number, then the bandwidth of each channel is significantly reduced. Therefore, to achieve high information capacity signal processing in photonics, which is also robust due to the topological degrees of freedom, we have to break the trade-off relation between channel number and bandwidth. The solution for this critical limitation is actually very simple. The utilization of the three-dimensional circuit, or the multi-layers of the two-dimensional circuit. However, such a circuit is actually very difficult to be implemented through the current state-of-the-art fabrication technology. Therefore, instead of utilizing three-dimensional circuits, we implement the two-dimensional lattice structures, which is effectively the same as the three-dimensional geometry. And this lattice overlap design can be implemented by the waveguide crossing structure between the optical element. Here, the optical element of each circuit is optical resonator. And then, by employing such a lattice overlap technique, we successfully obtain the increase of the channel number while preserving the bandwidth of each channel. Therefore, we successfully break the trade-off relation between the channel number and the bandwidth. And here is a key application of our design, multi-channel noise immune functionality. Noise immunity, or the defect robustness, is realized by the topological properties of our design. And the critical point is that we can achieve the multi-channel with sufficiently larger bandwidths than conventional topological photonic platforms. And because of this multi-channel functionality, you can obtain the light splitters. For example, if you excite 3 modes here, then you can obtain the splitting of 2 modes and 1 mode. The critical point is that because of the topological nature of our design, you can obtain strong robustness to the defect. Here is the transmission curve against the uniformly random defect in each optical element. And surprisingly, we can also control incoherent input because of the separation of 2 modes and 1 mode are determined by the topological nature at the junction of this structure. And here is the bottom line of our work is that we can achieve noise immune and multi-channel photonic signal processor for higher information capacity.